press conference with the flight crew from Space Shuttle Mission 51L, due to go up in January. I'll introduce the commander of the flight, Dick Scobie, on the left of the podium here, and Dick will introduce the rest of the crew. Go ahead.
It's a pleasure being here with you all this morning. This good-looking group off to my right, I'd like to introduce them one at a time by specialty, and then I would like each one of them to say a little bit about what they're going to do on the flight. So without further ado, Elson Onizuka is our expert on the tracking data relay satellite, the inertial upper stage, our largest payload on board. Ron McNair is our expert on the Spartan Halley, the Comet research satellite we're carrying on board that we're going to put out over the side for a couple days and pick up. Mike Smith, our pilot, who also backs me up on everything I do. He's also an expert in rendezvous, prox ops, and systems. Judy Resnick, who's our flight engineer, probably one of the most knowledgeable people on systems on the orbiter in the astronaut office, so she's a real asset to the crew. She is also our remote manipulator system operator, so she's a crane operator on the side. Greg Jarvis, who's one of our payload specialists. Greg has a flight dynamics experiment on board he'll talk to you about. It's fairly colorful, and it's a nice experiment to be performed on board the orbiter during the whole mission. And of course, Christa McAuliffe, our teacher in space, will be doing teacher activities the whole flight. So first off, I'd like to start off with Ellen. We'll just run down the line and everybody talk a little bit about what they do on the mission.
Well, the tracking and data relay satellite, commonly referred to as TDRS, is being launched on this mission using a large inertial upper stage booster. It's a solid rocket booster weighing just under 40,000 pounds. With the satellite itself, we have a package of approximately 45,000 pounds being deployed from the shuttle. This is the second of the TDRS satellites to be deployed. With this satellite on orbit, we will then have near global coverage using this satellite, which we will eventually place somewhere over the Pacific, and the satellite that currently is on station northwest of Brazil. We will be able to have almost complete global coverage for shuttle operations. The TDRS mission itself is quite involved. We will start our inertial upper stage checkouts beginning about 1 hour and 40 minutes into the mission. Working through the rest of the activities, our intent is to deploy this satellite approximately 10 hours into the mission. The satellite is presently undergoing tests at the Kennedy Space Center. The booster has completed its testing, and the satellite and booster will go through a final test at the launch pad sometime in early January, and we hope to be launching on schedule, on time.
The Spartan Halley spacecraft has the distinction of being one of the first in a series of free-flying satellites that will observe the comet Halley. The Spartan has flown on a previous mission. It carries many scientific packages, but the Halley scientific package will be one carrying instruments that will enable the spacecraft to determine where it is in the universe, where the comet must be, and aim its sensors at the comet in order to make measurements. The Spartan Halley will be deployed from the payload bay using the manipulator arm, and Judy will tell you more about that. And the orbiter will back away and return to retrieve it several days later, which Mike and Dick will be performing those maneuvers. But while the satellite is out there, we'll use its sun sensors to look at the sun. Then we'll use its star trackers to find a fixed star. And using that information and the data that I will be loading into it, Elle and I will be doing the Spartan preparation, then the Spartan will be able to fire its jets to maneuver around toward a comet, a small dot in the universe, and make very precise measurements. Now, comets are very much in the news now. I don't need to tell you much about the comets, except that they happen to be remnants of the creation of the universe, the origins of the universe, frozen gases of various types of gases. And scientists are interested in knowing just what are the components of a comet. What are the constituent gases that makes up the comet? And from this, we can get some idea about the origins of the universe, and these type of studies can sometimes change the way you think about things. So, consequently, we look forward to this experiment. It's not just a satellite that we kick out and forget about it, but it affords us, the crew, the opportunity to do many different things. A deploy sequence, we get to do some arm operations, we get to do some rendezvous and proximity operations, and it's an exciting one for us as well as for scientists at the University of Colorado, who happen to be the principal investigators. So Spartan, the Common Halley, we'll learn a little bit about it, a great deal about it, and enjoy doing it in the process.
Well, as Ron said, the Spartan is a free flyer, and that means that we're going to have to do some proximity operations and also a rendezvous to pick it up after it does its mission. And on flight day 3, Judy will put the satellite in the proper position over the payload bay, and we will position the orbiter in its proper attitude, and we'll release the Spartan late in the day, around 7 or 8 o'clock Houston time. Once the Spartan is released, we station keep on the satellite for about 10 minutes. We then do, while we're station keeping on it, the Spartan goes through some of its checkout maneuvers to make sure that its attitude control system is going to work correctly. If it doesn't work correctly, we'll pick the satellite back up and put it back in the bay, but assuming that it works, everything checks out correctly, then we'll do a burn to separate from the satellite. It takes us up and over the satellite, and then we basically just drift away from the satellite for 16 orbits, or about 24 hours. 24 hours later, we do a small burn that starts us drifting back towards the Spartan Halley satellite, and then we sleep for about 10 revs while we drift back towards the satellite. Then when we get up on flight day 5, we start our rendezvous maneuvers, a series of burns that brings us up about 500 feet in front of the satellite. At that point, Dick will fly the shuttle up to within about 35 feet, putting the Spartan Halley right over the payload bay, and Judy will pick up the satellite with the remote manipulator arm. Just before we get to the 500 feet from the satellite will turn on its lights and also maneuver to the proper attitude so that Judy can pick it up with the arm.
And I'll tell you a little bit about the Spartan and operating it with the arm. Spartan is a box that's about 4 by 4 by 4 feet. When it sits in the cargo bay, if you can imagine that I'm in the cockpit looking aft, it sits in the cargo bay like this, and the arm comes out and picks it up on its grapple fixture like so, and will actually maneuver it so that its sun sensor is pointing towards the sun, which is off the tail, and we'll let it out of the orbiter more or less like this, and it will do its pointing as Ron said, and we will fly away from it. And when we come back to retrieve it, once again we'll have the arm up, and it will be coming at us more or less like this, and hopefully with the plane in the right plane where the grapple fixture and the arm are lined up, and just grab a hold of it and put it back down in the bay. We're going to use the arm for a couple of other things on the mission, not quite as extensive operations as we do with the Spartan, but we are going to use it on day 1 to take a look at the firing of the inertial upper stage's first rocket motor, which happens about an hour after we let it out. We'll actually position the arm so that the wrist camera can monitor the ignition of that burn and watch it through its duration. We'll also use the arm before we deploy the Spartan to actually do a little survey of it in the payload bay to check that its experiment doors are in the proper configuration, and check the sunshade and the baffle area and make sure there's no ice or dust on it so that the experiment will operate properly. The other thing that I'm doing for the mission is being the third seat for ascent and entry. It's really the backseat driver for Mike and Dick. I'll just help them with nominal and any off-nominal procedures that they have. I don't throw any of the switches. They do all the switch throws, but I sort of keep track of what's going on.
I'll be conducting a set of experiments that investigate the effects of zero gravity on fluid motion. The experiment uses vessels that are scale models of propellant tanks that we use in the satellites built by Hughes. The first set of experiments document the fluid motion in both a spherical and conospherical tank. The second set of experiments uses a model of the spacecraft to investigate the stability of Frisbee dynamics with various amounts of fraction fill of liquid in the tanks. The third set of experiments uses the same spacecraft model in a free-flying mode in the mid-deck locker to gather data in a sustained zero-gravity environment, to correlate that data with data that we've obtained using drop test data in the laboratory.
And as the first space participant, I'd just like to say that I am very delighted to be part of this crew. Everybody's been wonderful in making me feel a part of this mission. I'll be teaching 2 lessons from the shuttle, and I was amazed to find out how much crew participation I needed for the 2 lessons. Everybody's going to be involved in the field trip through the shuttle, either trying to stay out of the way so that they can get a good camera shot, or actually helping me out or using the cameras. So it's a whole crew activity when the lessons are filmed. The 2 lessons will be downlinked live. And I think it's going to be very exciting for kids to be able to turn on the TV and see the teacher teaching from space. The first is going to be a field trip through the shuttle, and it will start up on the flight deck. And after I introduce the commander and the pilot and talk a little bit about the flight deck, I'll be floating down into the middeck and dealing with all of the things that have to take place because of a weightless environment. Why do you have to have things stowed a certain way, or the exercise that has to be done on board the shuttle, or the galley that is used, and how things are a little different, the sleep sack, or the bathroom facilities. And then the second lesson is, why are we in space, starting with the quantum leaps that we have made from the Wright brothers' flight up to the space station, which is our future in space. A lot of people, when I first started this whole venture and talking to them, really didn't have a good idea of some of the experiments that took place on board the shuttle or some of the satellites that were launched. So I'm hoping to bring that out in the second lesson. There'll also be some demonstrations that I'm going to be doing, and these aren't going to be live, but they will be brought back in 16mm film and will be scripted and sent out to the schools at a later date. When the 10 of us met as the 10 finalists in Washington, D.C. in August, we realized that we wanted something very visual that students could do in the classroom and look and see how it happened that a magnet, for example, was reacting in a weightless environment, and how it happened that that magnet reacted in a gravity environment. So there's going to be one on magnetism. The demonstrations, one of them is going to be on magnetism, and we've got a wonderful 3-dimensional magnet that we took up in the KC-135, and it just worked beautifully. So we're very excited about that. There's going to be one on chromatography, one on simple machines, just so that the students have an idea of whether simple machines would ever have been developed in space, because it certainly helps us do work on Earth. Another one on hydroponics. We're going to be doing something on Newton's laws, because a lot of teachers say it's very difficult to teach Newton's laws when you have gravity to contend with down here on Earth. And the last one will be on effervescence, just to see how bubbles react. So I'm quite excited in being part of this wonderful mission.